So, hello everybody. My name is Arnaud Devos, and in this talk I will talk about a product form solution for a two-class queuing model, and this is joint work with Michiel de Muynck, Professor Joris Walraevens, and Professor Herwig Bruneel. So, the system under study. We have two parallel queues named Q1 and Q2, and both queues have an infinite storage capacity. But there's only one common server, which means that at most one customer, so from either queue, is served during a slot. So we need a scheduling discipline, and it goes as follows. The scheduling discipline: the customers depart from the queues in a random fashion. The probability that a customer of the first queue can depart during a slot is given by alpha. And then the probability that a customer of the second queue can depart during a slot is given by 1 minus alpha. And this random decision is independent from slot to slot. And in this paper, in this talk, we assume a very specific arrival process, which we call the global geometric distribution, which I will explain now. So for the global geometric distribution, the total number of arrivals into the system during a slot is geometrically distributed with a certain mean. And this implies that the probability mass function of the arriving customers during a slot is given by this expression. So that is the total number of customers, and then each arriving customer is routed randomly to one of the two queues with fixed probabilities, these two probabilities, and this then implies, or that you can quite easily calculate the joint probability mass function of the arrivals into the two queues, and this is given by this expression. And I note that lambda t, which is the mean arrival rate of the total number of customers, is given by the sum of lambda 1 and lambda 2, and lambda 1 is the mean arrival rate in the first queue during a slot, and lambda 2 the mean arrival rate in a second queue. So this expression has in fact only two parameters, namely lambda 1 and lambda 2. So a very specific arrival process for this queuing model, and we can sketch the queuing model as follows. So we have this global geometric arrival distribution. At the input, two queues, and then at the output we have only one server which has to randomly select one of the two queues to possibly serve a customer. Okay, and then we look at the queuing analysis. So the system contents at the beginning of a slot k of the queues is defined by these two random variables, u1k and u2k, and the joint probability mass function of these two random variables is defined as pk, so is this probability. And then you can derive this equation of pk plus 1 in terms of pk. And if the stability conditions hold and we let the time parameter k go to infinity, then this equation becomes independent of k, and then we obtain what we call the balance equations. So the balance equations are just like this expression, but without the dependence on the time parameter k. Okay, and then we want to solve the balance equations, and we do that by transforming it to the z domain. So we use generating functions, namely a joint generating function. And if you transform the balance equations, you obtain actually a functional equation for the joint generating function. And it's an understatement to say that it is very, very difficult to solve this equation. It is well known in a particular area of queuing theory that it is very difficult. and you can solve this equation using the theory of boundary value problems. But yeah, it is very important to remark that explicit closed forms results for this kind of problems are usually rare. But yeah, I assumed a very specific arrival process in this model, the global geometric distribution, and it turns out that this is one of the rare cases, so for this model, where we can derive an explicit analytic expression for the whole joint PGF. And how we did this will not be the talk of this topic. The result of the solution will be the talk, namely that we find that the joint PGF is of product form, which implies that the system contents in both queues are independent, which is yeah, quite remarkable if you think about it. And before I proceed, just a minor remark. So here we are interested in the joint distribution, so in a sense in the correlation structure. But if you are only interested in the marginal system contents, then it's yeah, an easy problem. But here we are interested in the joint distribution, and it turns out that it is of product form. So the independence of the system contents will be the talk of this. Will be the topic of this talk. Why is this remarkable? So observe that the steady-state system contents in a queue are merely the result of the arrivals and the departures before the slot that you observe. And the arrivals, so a very specific arrival process, so we can compute the correlation coefficient between the arrivals into the two queues during a slot, and that is given by this expression. And important is that this is always positive. So what arrives at the two queues during a slot is positively correlated. And then on the other hand, at the output process, so we have that at most one customer in the whole system can depart during a slot. So this implies that the number of departures from Q1 and Q2 during a slot is negatively correlated. So we have here positive correlation, here negative correlation. But yeah, why are the steady-state system contents independent? Can we explain this using simple probabilistic reasoning? And yes, we can. So assume that this is a possible sample path for the system. So in the first slot, we have in total 4 arrivals. 3 arrivals in the first queue and 1 in the second queue. Then we have 2 slots where there are no arrivals, and then we have a slot with 3 arrivals. And yeah, remind that we have that the arrivals, the total number of arrivals in a slot, are geometrically distributed. So the arriving customers within a slot arrive independent from customer to customer. This is the definition of the geometric distribution as you see it yeah, as the connection with Bernoulli trials. And next we will look at a different time scale. Yeah, and it looks like this. So we have now the consecutive events, namely the arrivals, and then yeah, when a new slot begins, so where a possible departure occurs. So from the rest of this presentation, we will reason on this time axis. But we will first adapt something else in this time axis. So when a new slot begins, a customer can be served, but because of the randomly alternating service, this is always independent from previous events, and there are 2 possibilities, namely that a customer from the first queue is served or from the second queue. So in total we have 4 different events, and all these events are independent from each other. So if we look at the changes of the system contents, then this is nothing else than a sequence of independent events. So for example, here it is given by this sequence of events. But yeah, to explain now the independency, I will use a different encoding. For these symbols, I will use numbers 1, 2, 3, and 4. So this corresponds to this sequence of numbers. So 1 and 2 are the arrivals, and 3 and 4 are the possible departures. And we will now observe system contents, but right after right after these events in steady state. And I define these system contents now as V1 and V2. And then the first observation is that only the numbers 1 and 3 are sufficient and necessary to determine V1, which is the system content in the first queue after such an event. And yeah, I think this is clear. If you look at these 4 events, that you only need 1 and 3, and it is also sufficient to determine V1. And the same holds true for the second queue, where you only need 2 and 4, and it is also sufficient. Okay, this is, I think, very clear. And then the other observation, so observation 2a, is that information of V2, and hence information about the occurrences of the events 2 and 4, this gives us no information about V1. So this is important and maybe not immediately obvious, but assume that you know at some point that the evolution of V2 is given by the sequence 2, 4, 2, 2, so in that order. And if you know this, it gives you no information about the possible occurrence of the events 1 and 3. And by which I mean the order and amount. So between these numbers, or before these numbers, or after these numbers, you have no clue about the occurrence of the 1s and 3s. And this is quite strong, and it's because these events are independent from each other. And maybe to illustrate it more, assume in contrast that it is not a global geometric distribution, but that we have at most 1 arrival during a slot, which is then either an arrival in the first or in the second queue. And this is now to illustrate that this is not obvious. So if you assume now this other arrival process with at most 1 arrival, then an event 1 and 2, which are the arrivals, must then be followed by an event 3 or 4. So arrival must be followed by a possible departure, because you have at most 1 arrival during a slot. So, and for this different arrival process, if you there know at some point the evolution of V2 is given by the sequence 2, 4, 2, 2, then you see here, okay, I have 2 2s, but a 2 must always be followed by a 3 or a 4. And this 2 is not followed by a 4. So here we know, okay, between these two events 2, there must be at least 1 event 3. So in this case, you do have some partial information about the occurrence of the events 3. So, and this means that for this arrival process, the arrivals into the second queue and the departures into the first queue are no longer independent in this different time scale, of course. So this is to illustrate that what we have for the global geometric distribution is very special and not obvious at all. Okay, and then of course we can do the opposite. So the information about V1 gives us no information about V2. So, and together with our observations, we can conclude, okay, V1 and V2 are independent random variables. And then we use the Basta property. So Bernoulli arrivals see time averages So the events 1 and 2 are Bernoulli arrivals within the definition of a geometric distribution, of course. And from the basta property, it follows that also the random variables u1 and u2 are independent, which, yeah, these two random variables were the system contents at the beginning of a random slot in steady state. Okay, so yeah, this is the intuitive proof. I hope you appreciate it. The advantage of this proof is that you can use it to extend your model to a more general model, which would not be possible with a pure mathematical proof. So thank you for listening. This was my presentation.